Welcome to a video introduction or background on laboratory number 5 for online chemistry at Goodwin College. So this lab begins on page 99 of your lab manual. Um, However, your lab manual is a little bit confusing and there's a fair amount of information that you don't actually need. So what this video is for is it basically provides background sort of explaining the ideas behind the lab that you're going to do. At a later point today, I am going to put out hopefully a more easily understandable set of directions for how to do this lab. So this video is just for the ideas behind the lab. At some point later today, I'm going to publish a set of instructions, probably in PDF form, that you can follow instead of following from page 99 onward in your lab manual, because I think it's a little too complicated and it's not very well written. So here we go. The first thing I want to talk about is light. And for some of you, this may be information that you already know about. For others of you, it may be information that you've never heard about. And some of this information you're just going to have to take on faith as the stuff that I'm telling you. So the first thing is that I'm sure you're all aware that light can come in different colors. There's white light, and there's basically every color of light that you can imagine. And usually the different colors of light that you can see are shown as a rainbow. So there's violet light, there's blue light, green, yellow, etc., etc. The first thing I want to tell you is that every color of light has a different amount of energy associated with it. And again, this may be news to you, it may not be news. If it is news to you, you're just sort of going to have to take it on faith that every different color of light has a different amount of energy associated with it. What I mean by that is that violet colored light, or purplish light, has a higher energy than blue light. So this over here, this part of the rainbow, is violet colored light. And what I'm saying is the energy associated with a certain amount of violet light is more than the energy associated with a certain amount of blue light. Turns out that blue light has more energy than green light. So if you have a certain amount of blue light, it has more energy than an equal amount of green light. And this is true as you travel on the colors of the rainbow in this direction. So green light has more energy than red light. So here's green light in the middle of the rainbow. If you have a certain amount of green light, it has more energy than an equal amount of red light. Just as a different example, ultraviolet light has really high energy. So the ultra in ultraviolet means that it's even beyond violet. So this was violet light over here. Ultraviolet light, which you can't really see, is off to the left here. And sometimes this is abbreviated UV light. UV light has so much energy that if you're exposed to it for too long, it can damage your skin and other biological tissues, which is why you're supposed to avoid UV light. And part of the reason why it's so dangerous is because it has a lot of energy associated with it, even more than violet light, even more than green light, even more than red light. So that's sort of the first piece of information that I want you to have under your belt. Different colors of light have different amounts of energy associated with them. Now we're going to take a detour, but we'll come back to this concept in a few slides. The next thing I want to talk about is stairs, which I'm just sort of trying to be funny here and calling it Stairmaster. So imagine that you're standing at the bottom of a set of stairs, and if you climb up one step, it takes a certain amount of energy. You have to put in a certain amount of energy to climb up that one step. If you then stand on the edge of this step and you fall back down, you will release a certain amount of energy as well, because you have a certain amount of, actually it turns out to be potential energy, because you're standing on this higher ground. And if you fall back down, you'll release a certain amount of energy. If it's a small step, you won't release very much, but you'll release something. Now imagine that you have a different set of stairs. Here are the stairs over here. The distance between each step is much bigger than the distance between the steps over here on the left. So if you were standing here at the ground and you climbed up one step, you would actually have to put in more energy to climb up that larger step. And if you stood on the edge of this step and you fell over, you would release more energy than you would if you fell down a little step. The extreme example of this, if this doesn't sort of make intuitive sense to you, the extreme example of this is that you could imagine that you could climb up on the roof of a building, and you could think that going down from the roof of the building to the ground is one very large step. If you fall down that one very large step from the roof of a building to the ground, you will release a lot of energy. In fact, probably so much energy that it will break many bones in your body. But the punchline here is that if you fall down a large step, you will release more energy than if you fell down a little step. So again, keep that concept in mind. The reason I'm telling you that is the following. It turns out that electrons in an atom, they climb and fall too. But they don't climb and fall steps. You can think of them as climbing and falling on different shells of the atom. So this is related to the idea of shells that we talked about in earlier units. So you can imagine a pretend atom here. It doesn't really matter which one it is. But you can imagine that this atom has some electrons in its first shell. It also has a couple of electrons in its second shell. And so you could imagine that this electron over here could conceivably, if you gave it enough energy, climb to the third shell. That would be the equivalent of having this electron sitting here and climbing up one step. So if we give this electron a certain amount of energy, it can climb up one shell. And so I'm going to show that here in animation form. It's going to climb up to the third shell here, and here it's going to climb up one step. So here goes the animation. There, we gave it enough energy and it climbed up. It turns out that you can actually do this to electrons in atoms. However, they don't spend much time at this new level, at this new shell. When they are at this new level or at this new shell, there's a formal term that's used. You say that the electron is in an excited state. I don't expect you to know that, but just in case I lapse into that, just in case I start using that word in this lecture, you can think of it that way. So there's the electron in its excited state, but it doesn't last there very long. It actually falls back down. So I'm going to make it fall back down in a second, and it's going to fall back down the step here. However, on the previous slide, we said that if you fall back down a step, you're going to release a certain amount of energy. And so that's what the electron is going to do. It's going to fall back down a shell, it'll fall back down a step, and it'll release a certain amount of energy. But the way that it's going to release the energy is special. The way that it releases the energy is that it emits light. So this electron is going to fall down a step, and let's watch the animation. Falls back down, and it emits light. However, because it fell down a certain amount, and because it released a very specific amount of energy, it will release a certain color of light, because different colors of light have different amounts of energy. So in this case, we said that just as an example, I'm basically saying that the light that was emitted when the electron fell back down from the third shell to the second shell was red light. The reason why I had it be red light is because, if you remember from the first slide, red light doesn't have a lot of energy, and here the electron fell down a little step. So it released a little bit of energy, and so it released red light, let's say. The idea is that different atoms, although they may have the same types of shells, the spacing between the shells in different atoms is different. Another thing to point out is that when the electron falls back down to its original shell, you say that the electron is in its ground state. Again, you don't need to know that, but sometimes it comes up. So the idea is that different atoms, they might have the same types of shells, but they have different spacing between those shells. So here's an example. Again, let's not get caught up in what kind of atom this is. This is just basically for illustration of the point. Here, this atom has a first shell, a second shell, a third shell, etc. But here the spacing between the second shell and the third shell is a lot bigger. So this is equivalent to having much larger steps. So if we gave this electron enough energy that you could send this electron in the second shell to the third shell, that would be the equivalent of climbing one large step. But again, it's not going to spend a lot of time in the third shell. It's going to fall back down to its ground state. But first, let's excite the electron. Let's have it go from this step to the next one, or from the second shell to the third shell. There it goes. It's in its excited state. But then almost immediately it falls back down. If it falls back down this large step, it's going to release a lot of energy. However, because it's releasing energy as light and it's releasing a lot of energy, what it's going to do is it's going to emit light of a different color. Again, because different colored light has different amount of energy associated with it. So here the electron falls back down and it releases light, but let's say this time it releases purple light because purple light or violet light has more energy than red light. So that's basically the idea behind today's lab. I'll explain it in a little bit more detail. But the punchline is that different atoms, because they have different spacing between their shells, will emit different colors of light when you excite their electrons. And so there's the ground state again. Just to emphasize this point again, I'm going to say it in a different way. If I excite an electron from a sodium atom, when the electron falls back to the ground state, it will emit a different color of light than an electron falling back to the ground state in other types of atoms. And the other punchline here is that every type of atom has its electrons emit different colors of light than other types of atoms. So the type of color that different atoms emit, you can use that as a fingerprint for your particular type of atom. So sodium will emit certain colors that are unique to sodium. Calcium might emit different colors that are unique to calcium, etc., etc., etc. You can use those colors to try to identify what type of atom you've excited. So who cares? I know that probably most of you, this isn't terribly interesting. This actually turns out to be used in the real world a lot. For those of you who follow the news at least a year or so ago, you may be aware that we, the United States, has sent a robot to explore Mars, and this robot is named Curiosity. So this quote is taken from the New York Times, but it's relevant to what we just talked about. Recently, Curiosity has been busy vaporizing Martian rocks and seeing what they're made of. On Sunday, the rover fired a laser instrument for the first time, hitting a rock with 30 bursts in 10 seconds and analyzing the atomic makeup from the resulting flashes of light. So we've basically got this robot on the surface of Mars, and the way that we are figuring out what the rocks on Mars are made of is by exciting the electrons in those rocks and seeing what colored light is emitted, because we know that sodium emits one type of light and other elements emit different types of light. So you can basically just analyze the color of light that's emitted and try to figure out what materials they're made of. This idea is used in other real-world situations too. When you see different colored fireworks, the principle behind that is what we just talked about. In other words, if you want fireworks to emit a blue-colored light, you basically add a certain type of element that when you excite the electrons in that element, it will emit blue light when the electrons fall back to the ground state. And if you want your fireworks to emit a different colored light, red or orange or something else, you have to add other types of chemicals that will emit different colors of light when you excite their electrons. So that's the idea that we have just discussed is basically how different fireworks work as well. If you follow astronomy and you listen to reports sometimes, astronomers will say, well, we know that star that's a zillion miles away is made of the following elements. And then you can sit there and say, well, how do they know that? The reason they know that is because we have basically analyzed most of the elements in excruciating detail, and we know what type of light each element emits. And so if you look at the type of light that different stars emit, you can basically figure out what type of elements are in those stars, even though you can't travel to those stars and take a sample. This is also true when people are trying, the same principle generally applies sometimes when people are trying to figure out where a bomb was made or what a bomb was made of if there's a terrorist bombing. So you can take samples of the residue of a bombing and you can basically excite the electrons in the chemicals in that sample and determine what type of materials went into making those types of bombs. So the general principle that we've been talking about exciting the electrons in an atom and then analyzing the type of light that it emits, applies in a number of settings, although usually it's a little bit more sophisticated than the way that I've just described it. The principle is the same. So the lab that you're going to do for this unit is basically exciting the electrons in certain atoms and seeing what color of light is emitted. So the lab for today, really for this week, sometimes it's called a flame test lab. It's a little bit dangerous because you're actually setting things on fire. In your case, you're going to use a candle. You're going to light different materials, different chemicals on fire, and observe what color they emit. So the way that you are exciting the electrons is to basically set the material on fire and add energy that way. Then you're going to see what colors they emit, and you're going to see what different materials emit as far as colors are concerned. So that's basically it for the introduction. I'm going to put out a more detailed version of what you need to do in PDF form in a little while.